So let us talk about the greenhouse effect. The greenhouse effect. All right, I give you a simple explanation. To start with, how does it work? It's based on radiation. Okay, it's based on thermal radiation. And it's based on the fact that we have a layer of greenhouse gases in the atmosphere. So I produced a little sketch here. Okay, so the sketch includes the sun, which emits solar radiation downward towards the surface of Earth. This solar radiation passes through the layer of greenhouse gases. So the greenhouse gases do not absorb solar radiation much. Okay? So that's one thing. So the Earth's surface emits terrestrial radiation, shown here by the blue arrow, upward. This is the infrared or long-wave radiation emitted by the surface. Okay? However, the greenhouse gas layer absorbs some of the terrestrial radiation and then radiates a part of it out to space and the other part as back radiation back to the surface. So we can now have a very simple, straightforward conclusion. The surface of Earth receives solar radiation and back radiation. It's not only solar radiation, but also back radiation. There's a higher thermal energy flux, and this makes the surface warmer than without greenhouse gases. Okay, so this is the concept. This is the concept of the greenhouse effect. And indeed, we can prove that that it exists and how it works and how it will change. Okay, so now in order to understand this effect, we have to go into the details. So now, if you have a surface emitting thermal radiation, it emits the thermal radiation across a range of wavelengths. Not only one wavelength, but a range of wavelengths in something that we call a spectrum of thermal radiation. And this sketch here shows a range of spectra, okay, as a function of different temperatures. For example, the outermost line here shows the spectrum for solar radiation, corresponding to 7,000 degrees Kelvin of surface temperature. Okay, you see the spectrum, and the key feature is that you get a maximum intensity around a specific wavelength. Okay? All right. If you change the temperature, which is shown here as in other examples, if you decrease the temperature by 1000 Kelvin or 2000 or 3000, this maximum actually moves to higher wavelengths. Okay, so there's a few key messages in here. Okay, the total energy increases with the temperature. Okay, so the intensity increases with temperature, and the peak wavelength decreases with temperature. All right, and these are theoretical curves, okay, and they're fit theoretically perfect to the true distributions, and we learn if we compare this with the true distribution of thermal radiation. So let's have a look at the solar radiation spectrum. Okay, it's shown here. So on the one axis here, on the x-axis, we have the wavelength in nanometers, shown in nanometers. That's the unit here. Okay, increasing to the right. Okay? And on the y-axis, we show the spectral irradiance. It's watts per square meter per nanometer range. So essentially, to get to the total radiation, you have to integrate across the spectrum. Okay? For each value you have to take the sum and integrate everything, the entire area that you have under this graph. So there is a theoretical curve, which is called the blackbody spectrum, shown here, for a temperature of 5,250 degrees Celsius. And that fits the true spectrum best, this temperature. And we have the sunlight spectrum at top of the atmosphere, which is actually the yellow orange bit. Okay? But this is not what arrives at the sea level, at the sea surface. What arrives at the sea surface is different. And this is the red curve. Okay, and this is the red curve. All right. And before I discuss now the details of this red curve, let's just start here with a summary. Solar radiation spectrum, okay, the peak of that is in the visible part of the spectrum, at wavelength in a range between 0.4 and 0.7 micrometers. Okay. So now what happens here is that there are gases that absorb radiation in specific absorption bands. Okay, in specific bands, and it's named here as water vapor. You can see takes away solar the energy flux at specific bands. There are quite a number of bands here, and this band, this band, this band. You can see CO2 has a little influence here. Okay, so gases absorb electromagnetic radiation in specific absorption bands, and you can see that ozone and water vapor have the biggest influence on the solar radiation spectrum. The key components of air, nitrogen and oxygen, do not absorb radiation. So that's sort of a lucky feature here. And also featuring ozone, which absorbs the dangerous UV part of solar radiation. Okay, this is how it looks like. All right. So let's have a look at the terrestrial radiation. Okay, the surface, because it has a temperature, the surface of Earth emits electromagnetic radiation. And let's see what happens to that radiation. Okay, this is shown here. Again, we have a theoretical line, which is shown by the red curve. Okay, get the mouse going here. By the red curve. Okay, so the terrestrial long-wave radiation peaks in the infrared part of the spectrum at wavelengths between 5 and 15 micrometers. Okay, so you have the theoretical part, but what arrives at the top of the atmosphere, so you now have to think the other way around, because the Earth emits radiation to space, is only undisturbed in a region that we call the atmospheric window. Here you really have the feature that there's a little interference of absorption in this so-called atmospheric window. Okay? The gases now that absorb the long-wave radiation emitted from the Earth's surface are called greenhouse gases. Okay, and you can see the key greenhouse gases are CO2. Okay. You have water vapor. You have, here in this range too, you have ozone. And you have methane. They are listed here. And you can see that they block or absorb some of that terrestrial radiation. All right, and that introduces you to greenhouse gases. Okay. And now a little summary. It's shown here a summary. It shows you the downgoing solar radiation and the upgoing thermal radiation by the Earth. in a combined graph. You can see the sun here, the Earth on the other side. And they are normalized because, you can't show them both on the same and realistic scales because the Earth, the sun's radiation is so much bigger than the Earth. Okay, anyway, but it shows here the theoretical curves for the sun and for the Earth. Okay, and for the Earth you can see 3 curves because it's just theoretically you can shift. The temperature. Okay, make it warmer or make it colder to see what are the potential influences on that. Okay. All right, and then you can look at what actually arrives at the surface of Earth in terms of solar radiation. And you can see that between 70 and 75% actually ends up at the surface. Okay, so there is a loss of 25 to 30%. Okay, due to absorption. And for the Earth, you can see how much is actually transmitted back to space, and we can see that only 15 to 30% is actually transmitted. So there is a large amount of thermal radiation from the Earth which is actually absorbed by greenhouse gases. And then you can look at the details. And below the second level, you see the total absorption and scattering expressed in percentage. 100% means that all of the radiation is absorbed, and low values means that this is where little radiation is absorbed. And highlighted are the key parts of the spectrum in red and in blue. Okay, and you can see the atmospheric window that I also introduced, and you can see that there's a and you can see that it's a big part is actually absorbed here of the thermal radiation. And now you can split it up into the components. And you can look at the absorption. Water vapor has a big role here at the higher wavelengths. Water vapor has a big role on both sides of the thermal radiation. Has different bands and has a little bit here with the thermal radiation. Oxygen and ozone. Oxygen and ozone, a little bit ozone, yeah. Oxygen has a little bit of an effect, but nothing big. Methane plays a role for the thermal radiation, as does nitrous oxide. Here you can see the different players, the major components absorbing terrestrial radiation, and seeing the difference between solar and terrestrial radiation. All right, and you can also see that the peaks of these spectra are actually occurring at different wavelengths. So they're not overlapping, and it actually means that the greenhouse gases, they operate differently on thermal and terrestrial radiation. Okay, featuring the atmospheric window. The atmospheric window is part of that spectrum of terrestrial radiation, which allows for radiation to escape to space. Okay, this is the atmospheric window. This is where the radiation escapes to space. But also within the atmospheric window, you can see absorption bands by specific greenhouse gases, including methane, nitrous oxide, CO2, water vapor, and also including CFCs. Okay, and there's a little list here, shown here, from the Hartmann book, and showing you the contribution to the greenhouse effect. Water vapor 55 to 70%, carbon dioxide 25%, CFC is 11%, methane 5%, nitrous oxide 2%, ozone less than 1%. So you get a feeling for which greenhouse gases are important. Okay? And we focus on carbon dioxide because, and indeed methane and nitrous oxide, because these are greenhouse gases that humans emit into the atmosphere, that actually changes the absorption or the total amount of greenhouse gases absorbed by the greenhouse layer. So this brings us to the end of the second part of this lecture.